All right, so when we're talking about calibration in analytical chemistry or science in general, we can't really have that conversation without also including or considering quality control. And they're really intimately related, and they're sort of an iterative back and forth process. So our quality control plan will inform our method of calibration, but our method of calibration will also inform how we conduct quality control and what questions. When we talk about quality control, um, what I'm really thinking about here, and this has sort of been a theme in several of the videos so far, is what are we going to do with the data once we collect it? So what to do with the data? Um, this is the huge question, and it's probably the biggest question of this course, in at least helping you develop an intuition about when you need to be really accurate and precise and when that's not worth your time, energy, and resources. What are you going to do with the data? Is this data critical to the life of a human, meaning it's going to be used for medicine or pharmacy or something like that? Is this data critical for, say, computing the coordinates of the Mars rover, in which you are costing hundreds of millions of dollars of a mission? Or is this a rough titration to consider generally what the concentration of an ion is in water for your own general understanding of the system, right? Those are all very different questions, and they require different treatments of the data, and probably different collections of the data, and certainly different methods of calibration and different considerations of quality control. So this is always going to be your first question. And that's what I hope you walk away with, if you walk away with anything from this class, is to, anytime you're about to do a measurement, you really pause, take a step back and say, why am I collecting this data? What's its purpose? And am I choosing a technique that is true to that purpose? Or is it overkill, right? Or is it underkill? You're not doing enough for the end use of this data. And so what you're trying to do now is transition away as a scientist from somebody else telling you what tool to use or what equipment to use or what experiment to do, and for you to start thinking through of all of your options based on the data usage, the end usage. This is what I need to do. So what's an example of the motivating question of how the data is going to be used? I've got an example of just one that I've used recently in my life, and that has to do with how ethanol, in this case this is the molecule C2H5OH, which I have sketched up here, or at least I have the formula sketched up here, so this is ethanol. I'll just write ETOH here. How much ethanol, what's the ethanol concentration in beer or wine or kombucha? And I ask this question because I make all of these products myself via fermentation. And what I have is a picture of a homebrew setup here on the left. So this is let's draw this in. This is a way to make it at home, which is how I do it, versus the picture to the right, which is the Budweiser factory, which is sort of industrial scale production of a fermented beverage. In this case, it's beer, but it could just as easily be wine or like a fermented tea like kombucha. The question here, if we're both in a process, we're both producing the same material, but then we want to do a measurement of that material. We both want to measure the ethanol concentration in our products. How is our end use differing between me as a home brewer and Budweiser as somebody who commercially produces millions of gallons of this beverage and then sells it, but also is relegated to certain local, state, and federal, and actually international legislation or laws by which they're producing this material, right? And so the end use, even though we're doing exactly the same measurement, or we're not necessarily measuring it the same way, but we're measuring the same compound, we have different end uses. And so the different end uses justify a different means or methodology, in this case, perhaps a different set of quality control steps to ensure we're doing it the right way. So when we're making this consideration and we're thinking about how are we going to use the end data that we collect, there's sort of a series of things that we need to consider. So in developing our method, which when I talk about method and method development, I'm talking about the entire process by which we use to measure and analyze our sample. That includes sample preparation, so how we're going to collect the sample. That includes maybe even statistical design. So I'm going to do n equals 16 samples. That's part of our method development. That includes how we are going to do the measurement, so the specific methodology. It includes all the details of that measurement. It includes also the processing of the data, the statistical analysis of the data, and ultimately the reporting of it. So the method by which you're analyzing something in developing that method is all-encompassing. It's all of the things that go into that, and there's several things that we need to consider when developing our method. Ultimately, though, all of these are reflected from the question, what are we doing with our data? Right? That's the consideration, the underlying consideration. The metrics we need to consider, one is, well, what is our analyte? Analyte, you're going to hear that a lot in this class if you haven't already heard it a lot in other chem courses. Analyte's the thing you're trying to measure, which is why the name is analyte. It's the thing we're trying to analyze. When considering our analyte, what it is, in this case, we're trying to measure ethanol, right? It's a specific compound. It has specific functional groups. What are those functional groups? How should this thing behave? When we're considering our analyte, we also need to consider this other component, which is called the matrix. Not the movie. The matrix is everything in the sample that is not the analyte, sans analyte. So in the example of, say, beer in this case, if we're going with this continuous example, ethanol is one molecule in beer. Beer is really complex. As you can imagine, most foods are. They're composed of hundreds to thousands to tens of thousands of unique molecules from very, very small carbon, hydrogen, or hydrocarbon compounds like ethanol or methanol, all the way up to these really big, sophisticated, blocky, chunky proteins, amino acids, big oligosaccharides, polysaccharides, etc. There's lots of stuff in there, right? Not to mention dissolved gases, dyes, all sorts of junk that's in there. Ethanol is the only analyte that we're trying to measure in this case. All that other junk is the matrix. And so when you're thinking about your method development and really how am I going to analyze my analyte, how do I find it, the matrix is more important than the analyte itself. What's all that other stuff there? And will my process, will my method be sensitive to my analyte even in the presence of all of these other molecules, right? And a lot of the times the answer is no, it won't be. And so in choosing methodologies, it's often matrix specific, right? Sometimes you might have to do a separation first. Sometimes you might have to do a filtration. Sometimes you might have to centrifuge your sample before you can get it away from some of these other interfering species in your sample. In line with that, the consideration of analyte matrix is this notion of selectivity, which is, again, really core to our considerations of how we're going to choose and develop a method of analysis. And so selectivity is the ability to select for or parse your analyte from the rest of the stuff. So ability to differentiate, and in this case, differentiate from similar compounds, right? A good method development is going to be one that's really robust to the presence of other molecules that are really similar, either in size or shape or functionality. And so in the case of ethanol, which is this C2H5OH, is your method good enough that it can differentiate ethanol from methanol, which would be CH2OH. or CH3OH. Not all methods can differentiate between those two things, right? And so selectivity is really important. In my research lab, I do a lot of analysis of metal ions in water in an effort to develop ultra cheap and affordable open source sensors that everybody can use, especially for communities that can't afford those sorts of things. And often I'm dealing with selectivity issues in developing these sensors where I need a sensor that can measure something like lead, but in the presence of, say, copper 2+, which is a similar size ion and charge ion, it can differentiate. It's not going to see copper and think it's lead. So that's when we're thinking about the development of our analysis. We need to consider these things. These are really important. What's in my matrix? What else should I expect there to be there? And will my method differentiate it? And do I care? Do I need a method that can differentiate it? The next criteria that's helpful in considering is this thing called sensitivity, which is very different than selectivity. So sensitivity has to do with when you calibrate your tool. So when you calibrate an instrument, you've all done this, whether you remember or not, in say a 107 or a 108 course, right? If you wanted to calibrate a spectrometer, you would have your spectrometer. It looks like this. If you remember back from Chem 107 or 108, these things are Spec 21s. You take and put your cuvette inside of there. You've got a lamp over here. It shines light through your cuvette with your sample in there, bounces off a detector, and then we read out some absorbance here, right? And when you're doing that calibration, you're going to run a bunch of different standards of differing concentrations. Maybe you run it at 1, 2, 5, and 10 milligrams per liter, each one being progressively darker in color, and you'd run them on your tool right there. When you do this, you generate a calibration curve, right, where you have absorbance versus the concentration of whatever that dye is, that thing you're trying to measure, and hopefully we get a nice straight line. We'll make plenty of these in this class. You'll make them with your home-built spectrometer as well. When we're talking about sensitivity, we're talking about, is our method, our tool that we're using to measure, how sensitive to it? Meaning, whatever the instrument is, it's spitting out some response, right? That's the whole basis of analytical chemistry and instrumentation. Is we take our analyte, we put it into the instrument, and then it tells us some response. And the goal is that response is proportional to the concentration of that analyte. That's the whole basis of calibration. In a spectrometer, absorbance is our response. That's our response that we're getting from the instrument, and we hope that it's linear as a function of the concentration of the analyte. And we know that's true because of the Beer-Lambert law, which tells us it's linear. Absorbance is proportional directly to concentration in that case. But not all tools are created equal, right? The Spec 21 may have a line that's nice and straight like this, but we have several spectrometers in the department, and you're going to have one that you do this with in your lab kits that's homemade using the sensor on your camera phone. And so the line's probably always going to be straight because that's defined by a fundamental property of matter and light based on the Beer-Lambert law. But your phone might give you a higher absorbance for the same concentration of a sample than the Spec 21. Or we could use a research grade spectrometer, and maybe that gives us even higher response for the same concentration, in which case the line is still straight, but it starts to get steeper with each tool that's more and more sensitive. So I'm running out of line colors here, but the slope of our calibration line tells us how sensitive our method is to our analyte, right? Because at the same, if we were to look and sort of think about each one of these points, they're all at the same exact concentration here on the x-axis, but they're giving progressively higher responses for that analyte. And so we would say the red line here is the most sensitive, and the black line at the bottom is the least sensitive. So sensitivity just has to do with, well, how responsive is our tool or our method to the analyte itself. So I'm going to put responsiveness here, and then considering calibration as actually really the slope of the calibration curve as a direct measure of sensitivity. We haven't talked about detection limit explicitly yet, but you'll compute this. It's an absolute fundamental parameter. So if we go back to the example that I just did, where we had absorbance versus concentration, and we're looking at this generic calibration curve, what's the bottom end of this calibration curve? At what point, if you keep diluting your sample, say this sample 1, we just keep diluting that and making that even more and more dilute by doing serial dilutions, at what point when you inject that into your method, whatever it is, it could be a spectrometer or another instrument or a titration or whatever, at what point is your method no longer sensitive at all? Meaning you have zero sensitivity, nothing changes when you change the concentration. That's the detection limit. That's the bottom end of your method, where you can keep going lower and lower and lower and lower, and it doesn't matter because your method doesn't see it. Right? That's critical. Right? You need to know that about your tool, because so I'll just write this as the bottom end. Mathematically, the way we actually calculate the detection limit is from the calibration curve, and we'll call this often the LOD for the limit of detection, and that's going to be equal to 3 times the standard deviation. And here we're talking about the standard deviation of our standards, whatever we ran, this group of standards, their standard deviation of the Y value of those standards, meaning the absorbance value that was measured in those standards. And I'll show you in a second how to compute that, divided by the slope of whatever your calibration line is here. So rise over run. That's the computational way to do it. There's several different ways to do that, but this is the easy, simple way to do that. To compute the standard deviation of Y values, standard deviation of Y, the Y values in the standards, in their standard set. In Excel, we use this term equals STEYX parentheses, and then highlight whatever those value, your standard absorbance values in that case. What this stands for is the standard error in Y of the X variable. That's what we're doing. Essentially, we're looking at the error in the Y dimension and whatever response units are that we have here. So if you imagine the LOD here, S is going to have units of whatever the response was. So in this case, absorbance. And then think about the units of M, right? This is going to be rise over run, which will be absorbance over concentration. So we'll end up having LOD equal to 3 times something with units of absorbance over units of absorbance over concentration. Those will cancel out, and we'll be left with an LOD in units of concentration. So M here, the reason why we use the slope is it allows us to convert our units between absorbance and concentration. So really we're talking about 3 times the standard deviation, and then M is just a conversion factor there. We'll talk more about this, but this is sort of setting you up here to start with. So similar to the detection limit, we also have the limit of quantitation. So detection means that we are still seeing a signal above that value, but that signal may not be large enough that we're comfortable to actually report it as a quantifiable value. We see it, it's a signal, but it may not even be linear at that point. The limit of quantitation is sort of our bottom end that we still quantify our analyte. Bottom end still quantifying. And the mathematical description there is actually really, really similar. We call this LOQ, limit of quantitation now, and this is going to be 10 times standard deviation over M. Standard deviation, again, being the standard error of Y in X, and M being the slope of the calibration curve. So these two values are really easy to compute. So we often report both of these. So if we do an analysis, it's important that after you do your analysis, and say you do a calibration, you get an equation of a line, y equals mx plus b, and you use the equation of the line to compute, say, the concentration of some real samples. Remember, this equation doesn't really consider for you whether or not this concentration that you're computing is a valid number. What you then need to do is consider, is my concentration in excess of my limit of quantitation? If it's not, then it's a non-quantifiable number. Is it in excess of your limit of detection? If not, then it's a non-reportable number. In that case, we would report it as saying less than LOD, or sometimes people would say NA because you couldn't quantify or measure that value. That report is very different than reporting something as 0. It's almost impossible to ever report anything as 0 because that assumes we can measure 0, which we can almost never, right? We can measure small amounts of things, but we can't measure the absence of things completely. And that's sort of a mind-bending thing to consider. So in chemistry, you are almost never reporting 0 for anything because the chances are it's just really small and we don't have tools to measure it. Instead, you're reporting less than the LOD and you're reporting what the LOD is. So the user, whoever's interpreting your data, can say, okay, it's a small number that's going to be less than, say, 1 part per billion, meaning they were unable to measure anything less than 1 part per billion. Doesn't mean it's not there, it's just less than 1 part per billion. Distinct difference, so you want to make sure you're clear on that bit. So as I said before, when you're doing an analysis, you are always, your tool or your method is always responding to your analyte. That's the whole goal. It's designing a process that is responsive, and if you're good, you're ideally responding, your response is linear with the analyte concentration, just because humans, we don't like to work in anything but linear space. We're bad at thinking logarithmically and exponentially. So for example, if we just draw up another sort of calibration response here, we would have our response over here. This could be anything. It could be intensity, absorbance, voltage, current, charge, whatever our technique is monitoring as a response variable as a function of the concentration of our analyte, right? That's the calibration curve. When we're thinking about our development of our method, we need to consider the useful range of our method. And really what we need to consider is, well, what range what concentration do we expect our analyte in our samples, right? You sort of have to know the answer to this, or at least an estimate of this, before you ever do the analysis, right? It's really difficult if you have no idea what concentration you're roughly shooting for. It's difficult to design a methodology for that. So for example, if you're trying to measure lead in drinking water, a good reference, a good rule of thumb is that the EPA mandates that lead needs to be less than 15 parts per billion in drinking water samples. This is the lead and copper rule. So when you're trying to measure lead in drinking water samples, you're probably measuring in the low part per billion range. So you need a tool that has a detection limit well below part per billion range, and you have to have an expectation of where your samples are going to lie, probably in the part per billion, maybe the part per million range if you've got a really contaminated sample, but certainly not any higher than that unless you're measuring something like acid mine drainage or the dissolution of lead paint in old houses or something like that. So the answer here is you have to have some idea. And then you need to make sure your method has a responsive range where you expect your analyte to be. So we have a couple different ranges here to consider. We have our linear range, and then we have this thing called the dynamic range. So when we are talking about the response, usually there's a portion of our curve, right, that as we're essentially at 0, of our analyte, which again is almost impossible to know or measure, but theoretically at very, very low concentrations, our analysis method is going to be irresponsive, meaning there's no response as we increase the concentration until we hit our limit of detection. Then as we hit the limit of detection, now our tool starts to respond. We get some response that increases as a function of the increased concentration of the analyte. And we start to increase, and hopefully this is a linear type response. So, but at some point, we start loading this thing in so much that our tool becomes oversaturated, and it can no longer respond in a linear way, and it starts to taper off and taper off and taper off until we flatline out right there. So this part of our response curve here, or calibration curve, we consider this the linear range. And that's the range, obviously, that the response is linear as a function of our analyte concentration. But all the way up to here, where the response eventually plateaus, it's important to note that your instrument or your tool, your method here, is still responding. The response is still increasing between here to here, right? It's just not doing it linearly. And so we call that full range the dynamic range. Dynamic meaning there's some change in response as a function of concentration. Beyond this, say out here and on, this is non-responsive. Meaning you can keep cranking up the concentration as much as you want and it's not going to change your response. The same is true in the region below the limit of detection, below the bottom end of our response curve. This is really important, right? Because many tools maybe have a range, or many methods maybe have a range on the order of a couple orders of magnitude. So by order of magnitude, I mean something like 10 to 100. So if you've got 2 orders of magnitude, maybe we can quantify 10 to 1,000 maybe parts per billion, right? So if you don't choose the right range for your method, because your analyte concentration needs to fall somewhere in that linear range. If it doesn't, if it falls up here or down here, useless method, right? It's not going to work. So it's really important. I will say there are some techniques out there, and if you're thinking about this from a research perspective, of course, we as chemists and as engineers are really thinking about how do we build tools that have huge dynamic ranges, right? How do we build sensors that are sensitive or even linear over like a 10 to the 7, like 7 orders of magnitude, a billion-fold. Right? Some of the sensors we create in my research lab are sensitive over roughly a million-fold change in concentration. That's really helpful because it means the user has to know less about their sample. They can just put a drop of water in there and it doesn't matter whether it's 1 part per billion or a million parts per billion, and it's still going to be responsive. But not all tools are created that way, and that's why when you're considering the method development, it's important that you're considering the range. Okay, so let's cycle back to our original consideration, our original problem, really, which is my problem, which is, you know, as a hobbyist or an enthusiast of fermentation, I like to make my own beer and wine and kombucha and sauerkraut and pickles and all the things that you do with home fermentation. And so when I'm measuring ethanol as my analyte, and I'm curious about its content in my, say, beer in a setup like this to the left. You know, if I go through these considerations and identify my analyte, my sensitivity, my accuracy and precision, my range, all of the things, and I choose the tool that fits for me, I don't need it to be overkill, right? And I don't have a ton of resources at my house, in my garage like this. And so the way that I measure ethanol for my data outcome, which is really just for me to casually know roughly what the alcohol by volume is in the beer that I make, I use this thing pictured down here. It's this thing, you may have seen this thing, it's called a hydrometer. And really, it's the thing on the inside here. The outside is just essentially a graduated cylinder, and there's beer on the inside. This thing is just, it's got a lead weight in the bottom right here, and then it's got a calibrated scale for density. And we know that as you add more and more ethanol to water, in the case of beer, the density is going to go down because the density of water is going to be reduced by the density of ethanol, which is less than that of water. And so we can calibrate one of these things. You can buy them for about $6 on Amazon. And for me, I'm saying that plus or minus 1% in terms of alcohol by volume is acceptable. This thing can probably do a little bit better than that. That can probably be roughly 0.25% that it'll give me, but that's it, right? It's $6. I can do this measurement on the fly when I'm brewing, and I get the numbers I want based on the usage of my data. But let's contrast that against this company, Budweiser, who manufactures millions of gallons of the same beverage every year, right? Their constraints are different. And in their case, they're constrained by this group called the ATF, or the Alcohol, Tobacco, Firearms Group, which is a government organization. And the federal mandate states that if you're going to sell one of these products, like beer, that you have to be able to report your alcohol by volume to 0.02% accuracy. So of course, their end use is going to constrain or inform the way they develop their method of analysis. And so certainly they're not going to simply use a cheap hydrometer from Amazon. They've got to use something different. And so they actually developed their own method that uses UV-vis spectroscopy. So let me tell you a short story about that process. So in 2013, believe it or not, but a large group, several thousand Americans, believed that Budweiser was watering down their beer. And they were so angry about this. This is all true. This was 7 years ago. They were so angry about this that they filed a class action lawsuit against the company Budweiser, because they believed that the concentration of ethanol was not what they said it was, that it was watered down. And so luckily Budweiser had internally created this really robust process for analyzing. Their method was really robust based on this 0.02% constraint. And so they went to court. They were able to validate their method to the court and to the jury, and they were exonerated from the claim. They didn't have to pay out at all. They found out that, in fact, their beer is not watered down. It just tastes really bad. And so that's a lesson, right? I'm not saying that corporations should be the victors here. I'm simply saying that the end use of your data dictates the method that you're going to choose for analyzing it. And I just showed you two really different ways to analyze the same molecule in a batch of a beer. And so that's really important, because most things in chemistry or biochemistry, you've got a whole plethora of techniques that you can choose, but you really need to consider what are you going to do with the data in the end, and then from that you go through a sort of method development analysis where you consider all of the variables that we just considered as we went through that set.